Hello, everyone. My name is Rachel Housego, and our research team includes scientists from Woods Hole Oceanographic Institution and personnel from the town of Duck and the town of Nags Head. We are interested in understanding how groundwater contributes to flooding on the North Carolina Outer Banks. You can see an aerial image of Duck, North Carolina here. The pier extends out into the Atlantic Ocean, and on the backside of the island is Currituck Sound. You can see from the aerial image that the island is low in elevation and densely populated. Houses span the entire width of the island. And this makes the community especially vulnerable to flooding hazards, such as the photo seen in the top right here. Many of you in this community will have seen the report that came out from NOAA last week describing the rise in incidents of nuisance flooding across the East Coast. Because of the low elevation of barrier islands, the water table is close to the land surface. Groundwater can contribute to these nuisance flooding events when the water table exceeds the land surface. The position of the water table also controls how much water the aquifer can absorb from rain or waves. And this has motivated our key research questions, which are: how does the coastal water table respond to precipitation and changes in ocean water level at the shoreline, driven by waves, tides, and surge? And can these ocean processes, without overtopping the dune, generate high enough groundwater levels to result in flooding in the absence of rain? And if so, where across the Outer Banks is this likely to occur? To address these questions, we've taken 3 steps. The first was to use observations to develop an analytical flooding model for the local region. The second was to use a citizen science flooding app to evaluate the model and expand awareness of groundwater flooding in the local community. And the last step was to simulate the location of flood-prone areas from large storms. To develop the analytical model, we're leveraging continuous oceanographic measurements maintained by the U.S. Army Corps of Engineers Field Research Facility in Duck, North Carolina. They have a wave and tide gauge both in the ocean and in the sound, and a weather station that collects precipitation data. In addition to these measurements, in September 2014, we installed a transect of groundwater wells that extends all the way across the barrier island. And in this aerial image, the colored circles indicate locations where we're taking groundwater measurements. The wells measure conductivity, temperature, pressure at 10-minute intervals. And this enables us to connect the changes that we're seeing in the ocean to the behavior in our groundwater wells. And you can see that by zooming in on a time series at these 4 wells closest to the ocean. Here in the top panel is wave height measured offshore, and the bottom panel shows groundwater head, and the color of the curves corresponds to the locations in the inset map. And what you'll see looking at this time series is anytime the wave height increases in the ocean, there's a corresponding increase in the water table. Following some of these larger events, such as Hurricane Joaquin and Hurricane Matthew, that increase in the water table could be up to 1.5 meters. Let's zoom in and take a look at one of these events in more detail. For this storm, the biggest head increase is at the well closest to the ocean, and the high groundwater level continues to propagate inland after the storm recedes. The maximum water level at the most inland well is measured 2 days after the peak at the well closest to the ocean. We developed an analytical model to describe the propagation of this bulge of high groundwater. The model is driven by the ocean properties and precipitation, and the rate of the propagation depends on the soil properties, such as the hydraulic conductivity or the specific yield. We assumed that the geology was uniform across the barrier, and comparing the predicted model behavior, the dashed line in this time series, to the observed behavior on the right, the analytical model does a good job of reproducing our observations. We evaluated the model for all of the storms in our time series and found that it's able to reproduce the maximum water level within 10 centimeters for all cases. Now that we established the model, we wanted to be able to validate it across the Outer Banks. So to do this, we designed a citizen science flooding app. We created the app to be simple to use and enable users to send us reports that includes information about the timing, location, photos, and survey responses that we can apply to validate our model. The app was advertised by the towns on their social media pages and in local publications, and the town personnel also were active users of the app and sent us many of our reports directly. We also advertised the app on the Citizen Science repository hosted by NSF and presented the app to the public at a local NGO chapter meeting. Between September 2019 and February 2020, we've received 35 reports from the app. And those reports are shown on the map here. The orientation is rotated so that north is directed off to the left, and the color of the markers indicates the depth of the flood report reported by the user. These reports span a 70-kilometer stretch of the Outer Banks between Duck and Rodantha, with the highest density of reports coming from Nag's Head. To validate the model, at each report location, we compared the predicted water table position to the elevation of the land surface, indicated here by the dashed red line, at the time of the flood report to determine whether the analytical model is accurately predicting a flood during that event. Here, the x-axis is the estimated initial water table position relative to the ground surface, and the y-axis is the estimated water table position at the time of the report. The shaded red region represents the model uncertainty. The shape of the symbol describes the amount of rain reported, and the vertical blue lines indicate the maximum water table within 1 day of the report. If the point falls within or exceeds the model uncertainty, then the model is predicting a flooding event that is consistent with the report. And we found that this is true for 75% of the cases that we analyzed, and that the model performed well for storms both with and without rainfall. Now that we have validated the model, we wanted to apply the model to understand where along the Outer Banks there might be regions that are vulnerable to groundwater-driven flooding during storm events. In this example, we were simulating a storm with 9-meter waves, which would be consistent with conditions during a hurricane or strong nor'easter. We calculated how much additional rainfall would be needed for an area to flood on the ocean side of the island. Regions in red are flooded just by groundwater alone. Pink require 10 centimeters additional rainfall, and regions in gray and black are unlikely to flood because it would require more than 20 centimeters of rain. The green circles indicate locations where we received flood reports, and again, north is oriented off to the left here. Based on this analysis, we found that approximately 11% of the area on the ocean side of the island would be expected to flood just from groundwater-driven processes alone in this scenario. We also identified 2 high-risk regions, one north of Duck and one south of Nag's Head. Moving forward, there are a couple of remaining challenges that we would like to address. All of our analysis assumes that the geology is uniform, so we'd like to better characterize the aquifer to determine where the model can be accurately applied. We'd also like to be able to update and revise the app as needed. Finally, we think there could be benefits to coupling our model with numerical simulations of ocean and sound water levels to do flood forecasting. In summary, we received 35 flood reports from the iFlood app. This enabled us to validate the model that we developed from observations at Duck across a 70-kilometer stretch of the Outer Banks. We found that the analytical model is able to reproduce the timing and location of these flood reports. We also have been very fortunate with the level of engagement that we have received from both the town offices and the local community, and that has greatly contributed to the outcome of this project. So with that, thank you very much for listening, and I'm happy to take any questions, and you can also contact me at the email address below. Thank you very much.